All right, so today what we want to look at are the indefinite integrals and the what we call the constant of integration. This is a concept that we've mentioned already, but I wanted to look at a little bit more formally here. And then also want to practice a little bit of integration by considering derivatives. You had a little bit of this kind of thing in some of your IP or some of the other practice, but we're going to look at it more and do some more complex ones today. You'll notice here I have this function f of x equals e to the 2x plus ln of x to the fourth plus 3x plus 5. And then I have a g of x that's the same except it has a minus 11 at the end, and h of x, which is the same except it has a plus 85 at the end. And I point out the fact that if you took the derivative of any of those, you would get the same thing. Okay, because that constant, the derivative, would be 0. So here, you'd have 2e to the 2x plus 4 over x plus 3 as the derivative, okay? Now, if we were to take the integral of 2e to the 2x plus 4 over x plus 3, which you'll be able to do by the end of tomorrow, if you can't already, you would get those same functions, f of x, g of x, h of x, except for that constant. And the reality is, when we're finding an indefinite integral, we express it as capital F of x plus c because we have all of these different possibilities. And we call that c the constant of integration. Okay? The constant of integration. Now, I want to look at this a little bit here, and I also want to take a look at an example of why the constant of integration is only significant when we're dealing with indefinite integrals. So we'll tie this back to what we were looking at with the fundamental theorem of calculus and see why we didn't bother with the plus c on any of those. Okay? So,
is that weird squiggly line supposed to indicate integration?
yes, that's that.
And that means had to find
The integral of e to the 2x plus 1 dx. Okay. All right, so here, if I were finding dy dx for e to the 2x plus 1, what is our derivative here?
To be e to the power of 2x plus 1 times 2.
Okay.
Or 2e to the power of 2x plus 1.
Yeah. Okay. Now, you'll notice here I'm trying to integrate e to the 2x plus 1. Well, you'll notice if I were to take the integral of 2 times e to the 2x plus 1, I would get this, right? If I took the integral of that, I would get e to the 2x plus 1. All right? So the idea here is if I can make what I have here look like what I have here, I'll know what it'll integrate to. Okay? So what do I need to do? What could I do? I have an e to the 2x plus 1. I need a 2e to the 2x plus 1. What should I do? There we go. Okay. We're getting the juices going this morning. All right, so am I allowed to just randomly multiply by 2?
No.
No. Okay, so what do I have to do? Divide by 2 as well. I need to counter that somehow, all right? But this is where those properties we looked at on Friday come into play. If I have a constant multiple, it doesn't matter if I put it inside the integral or outside the integral. So I'm going to put the times 1/2 outside the integral. All right? And now I know the integral of 2e to the 2x plus 1 is e to the 2x plus 1. but I have this 1/2 that it's multiplied by. And then I put my plus c. Okay? So the integral of e to the 2x plus 1 dx is 1/2 e to the 2x plus 1.
Why don't 1/2
plus
and
c.
2 just cancel out?
Well, they would. I mean, that's why we were allowed to do it, is because it would equal 1. But the reason why we put the 2 in here is so that it would match what we had over here. Okay? But the only reason we're allowed to do that is because we put the 1/2 outside as well. Alright, so you're right, it does cancel to 1. That's the whole point of why we're allowed to do it.
Sorry, why did you put the 2 in front?
So it would match this. Because I know this is the derivative of this. So if I take the integral of this, it would get me back here.
Yeah.
Okay? So I needed to make what was inside here match something I knew the integral of. Okay?
Oh.
We have a similar idea down here, okay? If I have y equals 2x plus 1 to the 4th, what's dy dx?
4 2x to the third times 2.
Which is 8.
Okay, good. 4 times 2x plus 1 to the 3rd times 2. So good, that's 8 times 2x plus 1 to the 3rd. Okay? So I know now that if I take the integral of 8 times 2x plus 1 to the 3rd,
1 over 8.
it'll get me back to that. So,
8 times 8 times 2x plus 1.
good, I need to put an 8 times there.
Yeah, and then 1/8.
A 1/8 on the outside.
So then the answer is 1/8 times 2x plus 1 to the third.
Not to the third.
To the fourth.
yes,
To the
To the fourth.
4th
Plus c.
plus c. Very good,
Why is
okay?
it to the 4th and not to the 3rd?
Well, because look at what we did. We took the derivative of this to get here, so if I take the integral of this, it'll take us back here. Okay? And that, in a way, is just like your x to the n rule. You add 1 to the exponent. Okay?
Are we trying to get it to match the derivative instead of just taking the antiderivative?
We're trying to get what's inside the integral to match the derivative over here. Because we know if we take the antiderivative or the integral of this, it'll get us back to here. That's why when we took once we got the 8 in here, we knew this whole integral equaled 2x plus 1 to the 4th.
So then why for the last example did we not have to add 1 to the exponent?
Well, because that was e to a power.
Oh, right, okay.
It's all in how the derivatives work
Okay.
as well. Okay? Okay, now I want to use this one here as a little example of why we didn't bother with the plus c when we were doing the fundamental theorem of calculus with a definite integral. Okay? Let's suppose I was taking the integral from 1 to 5 of 2x plus 1 to the 3rd dx. Okay? Now, we just showed that the integral of 2x plus 1 to the 3rd dx is 1/8 times 2x plus 1 to the 4th plus c. Okay? So I used our capital F notation here since we're going to be doing the fundamental theorem of calculus. How do I do the actual definite integral? The integral from 1 to 5? What? Good. Capital F of 5 minus capital F of 1. So look, here's capital F of 5. I have 1/8 times, that would be 11 to the 4th plus c. Okay?
Because that's the integral that he defined.
Okay? So we start with the upper bound here, 5. Now we have this lower bound 1, so it would be 1/8, and this would be 3 to the 4th. 2 times 1 plus 1, plus c. So notice here, when I do f of 5 minus f of 1, what happens?
C's gone.
The c's are going to cancel out. I'm going to have 1/8 times 11 to the 4th plus c minus 1/8 times 3 to the 4th minus c. Okay, distribute the negative, and those c's will cancel out. All right. So when you're doing a definite integral, we don't care about the c's. When we're doing an indefinite integral, we do want the c there. Okay? Any questions? All right. So let's try a few, okay? Can I have you guys try some of these? Don't forget there are ones that you can simplify a little bit, okay? Some of these you may, like this first one, and the second one you actually could use the rules we already know to do this. So if you can see how to do that, go ahead and do it. If not, then use the derivative. But down here, 7, 8, and the others, okay, on the next page, you'll need to use the derivative to help you figure out what the integral would be, okay? So let's use this time and practice some.